Yeah. Okay, but to get started, I shall introduce our panelists, and I suppose they can make their way to the stage as I introduce them. Starting with our speakers. Why are you giving me this look, Giacomo? Okay, Giacomo Guarnieri from the University of Pavia. Yes, thank you. You should have read your emails. Yes, so we have Giacomo, who gave us the lectures introducing quantum thermodynamics and introducing thermodynamic uncertainty relations to us. I remind everyone that the point of this panel will be to sort of like go over the lectures that we had this week and see how these topics align together, what open problems, interesting open problems do we have in the field, and just discuss how we feel this summer school went. And you guys, I will first ask some like 3 questions to our speakers, and then you guys can ask more questions. Following that, Dr. Philippe Feist from the Freie Universität Berlin, who taught us all about quantum error correction. Yes, nice clap, nice clap. Yes, 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 thank you, thank you. Let's go now for Dr. Mark Mitchison, PI of the Aspects Consortium, kindly funding us. Professor Natalia Ares of Magdalen College. No, All Souls. No, New College. Which college? Okay, New College, Oxford. Thank you, thank you. Who is also a PI in Aspects, will join us for this panel discussion. Let's welcome Natalia. Professor Gabriel Landi of the University of Rochester also joins us, who talks about metrology. We can also clap. Keep the claps going. Yes. And last but not least, to give us a more, well, in some sense junior, in some sense senior perspective on all of this, the good Sir Florian Meyer from Bern, who, okay, who is with us in the group of Markus Huber and Vienna, will join us as well for this discussion. Okay, so I would say a fun question to start off with. And indeed, this is a question that also the crowd may wish to give an answer to. So Mirko will be being made to walk to answer, should you wish. I would say a nice question to start off with is, what was a striking thing you heard in a lecture that you, I don't know, you found interesting? And I would say a lecture that wasn't yours. So if we could, I don't know, go through. Someone has an answer. Mark.
Sure. So I read your email, so I kind of thought about this before.
Nice,
so
nice.
Maybe that's why I go first. I don't know. I mean, I liked a few things. I liked. I actually really liked Gabrielle's statement about you know, the Cramér-Albin giving the true energy time uncertainty relation, even though that's, you know, something that I've seen before and I'm kind of well aware of, but I just, you know, I agree with it wholeheartedly. So I really liked that. And I also liked Ralph's statement about when he was talking about the connection between clock precision and entropy production and comparing with thermodynamic uncertainty relations, and the rather kind of strong statement that it's really the fundamental connection is between this accuracy parameter R and entropy production, and not the way that people in the stochastic thermodynamics community normally write it, which I'm not sure that I agree with, but I just liked it. It was it had chutzpah, so it was good. I liked it.
Interesting. Chutzpah, always good, always welcome. Does anyone else have anything they'd like to add? Maybe control. Do all the mics work on the table?
Guten Tag.
Okay.
Yeah, yeah, so I didn't give.
Maybe you need to speak German to activate.
Since I didn't give any lecture, I'm at liberty to say positive things about any of them. And I think somehow one of the striking things about the lecture in a field which I work in a lot, namely these quantum clocks, something I wasn't so actively aware of, and I think it's quite a cool concept, was this graph theoretic connection that Ralph was pointing out. And I think this also connects a bit to the lecture by Gabriel, where you somehow have stochastic trajectories and thinking of clocks also as devices or say systems that exhibit these trajectories. I think it's just a nice way to think about it. And to my impression, this has only been like, say, the community working on quantum clocks, they have only started exploring this in the recent years. So I think there's quite a lot to come from that.
Cool, and indeed, this graph theoretic perspective on Lindblad master equations is not even published. First to be exhibited here at the Calypso Summer School 2024. Is there anyone in the crowd that has something they found surprising a bit about the lecture that they would like to share with us? I guess not. That's okay. Right. So the school, I mean, titles, you know, what's in a name and all that, but the school was titled Precision in Quantum Information and Quantum Computation. And the three themes we had in the advanced track were metrology, quantum thermodynamics, and then quantum error correction. And some people might have found these three tracks maybe a bit disconnected. I would say they have connections across all three. Are there any questions across metrology, quantum thermodynamics, quantum computation, and also quantum error correction that you are currently interested in? Do you think that there are intersections in this field? Do you think that combining these fields and the approaches of the different fields is a fruitful thing? And would you like to comment on that? Whoever would like to go. Okay, Gab, thanks.
Yeah, so I think most experimentalists working in metrology, they don't care so much about the tools that we develop, the whole kind of Fisher information business. But I think it really opened up a lot, which has sometimes nothing to do with metrology itself, but just, you know, all of this idea of, say, information geometry that comes from Fisher information business. It's fascinating, and it's tools that can be applied in thermodynamics and in other areas. So I think the word precision is actually quite interesting, right? Because it is precision. I think it's a correct term, but it's not necessarily precision in the experimental sense that we're used to, but more precision in the sense of essentially kind of precision in Hilbert space. Let's put it this way, right? And I think that's I personally find that quite captivating. Like, I love Fisher information stuff, but to be honest, not really for its uses in parameter estimations per se, but for all of its kind of really cool ramifications.
Indeed. Would anyone else? Philippe.
Yeah, so I personally actually had a very large interest in all of the different topics, you know, that were presented in this school. So for me, this was like a perfect combination of a lot of different things that I've been interested in. I think we are in our field in quantum information, quantum computation, we have this luxury of being able to connect to so many different things. And because this field is still fairly young, right, compared to other fields that are around in physics and computer science and engineering and math. Because the field is still young, I mean, we've started seeing a bit of a splintering of maybe the quantum error correction crowd going into a more kind of focused subfield, maybe quantum information thermodynamics kind of evolving also into a more specific subfields forming within quantum information computation. But I think there are still a lot of connections to be made, and there are a lot of recent results that connect metrology to quantum error correction, whether it's like along the lines of the stuff I presented the other day, or whether it's simply for versions of the Easton-Knil theorem that was mentioned again today by Armanda, in terms of deriving limitations for what you can compute on an error correcting code. And it turns out that you can derive limitations that, and you have the Fisher information that appears, or you have a lot of recent results in near-term parameterized quantum circuits. You know, if you're interested in types of circuits that you can run on near-term quantum hardware, you might be interested in parameterizing them in a certain way. And then again, depending on what you want to do, the quantum Fisher information appears again. So I think, you know, it's not really a coincidence that these things appear, because a lot of these concepts, of course, are related. They're deeply rooted in the idea of thinking of information in terms of quantum information. But I think I'm really kind of happy that we still have this luxury of being able to connect all of very different concepts in the field.
Very cool. Natalia, I see you reaching for the mic.
Maybe I would like to add something, which is that I think in things like, you know, being an experimentalist and fighting, for example, things like error correction to the last, you know, saying, well, okay, what can we do with our systems that are so noisy? How can we do error correction? But also in the intersection with metrology and precision, you can think of saying, well, what are the tools that these other fields are giving us to even rethink what we are doing in terms of error correction and think what can we what are, let's say, the minimal functions of the devices that could help us to, you know, computation that might not be full quantum computation, right? But these things of stochastic computation, and we were talking about your paper about this. And I think that we might find novel ways of computing or even making our computing more efficient by using some of these concepts across fields.
Indeed, I would just comment that all of this, it makes me think of Feynman's grand challenge of building the smallest possible engine. What's the smallest possible engine you can build? And in some sense, a lot of the stuff we are doing, whether that's in the metrological context, whether that's in error correction, whether that's in computation, it's still taking that grand challenge of kind of like, what's the smallest thing? What's the sending the entropy to the smallest thing? It's still trying to answer that like long-standing grand challenge. And okay, we have some insights, but it's unclear how it will pan out. Yes, go ahead, Giacomo.
So yeah, in this respect, I think that what I really liked about this conference is like a sort of the fact that, as Felipe was saying, I mean, the communities of like error correction, information theory, and quantum thermodynamics, they are kind of like going in their own direction a little bit. They're becoming much more and more specialized, even though they are kind of young. And I think that this venue in particular, I mean, having the possibility to kind of like go back and I don't know, take a bird's eye view on this field, which I think has a lot of in common, no, between these kind of like subtopics. And I think the leitmotif is like information, really. So I mean, information theory is a very important thing, right? And manipulating information, like so doing operations that kind of manipulates information, like which is quantum computation essentially, is one aspect of that. But also like, I mean, information is physical, no, as the leitmotif says, and it has like a thermodynamic cost, no, when it kind of like involves equilibrium states and so on. And so thermodynamics plays a role. So I think it's important to keep this sort of like general perspective on the field because they are like similar, like different facets of the same coin, I would say. And yeah, so I really like this kind of like fact. And the fact that basically this also refers to what you said, because like if you kind of like aim towards building the smallest possible, studying what is the cost of, or what entails changing or manipulating the information at the smallest scale possible, then I mean, I think the message is that the fluctuations of these informations like that, I mean, all average quantities are not telling the whole story. And so, I mean, bounds like Cramer-Rao bounds, or I don't know, constraints like the Easton-Mill theorem on allowed transformations of information, or like thermodynamic, like TWARs, etc. I think they are kind of like all very related, and I like the effort to kind of put the crowd together and push together towards this goal.
For sure, I completely agree. And I think that's one of the very nice things about quantum information, really from the beginning, that brought different crowds together, and we should still keep that effort even within quantum information itself now. But indeed, you mentioned thermodynamics limiting computation. And this is also a question I asked in the Perspectives panel like 2 years ago at the first Calypso, which is like, does thermodynamics limit our ability to do quantum computation, right? Because quantum computation in principle is fully unitary. And I got a whole host of answers there, and I'd like your take as well. But before that, I'll just like sort of motivate this question a bit more to the crowd by saying that a lot of people, both at the table and in the crowd, have worked on things like how does the amount of entropy production processes producing limit the ability to sensitively estimate a parameter, whether that's time, so thermodynamics limiting our ability to keep track of clocks, or whether that's other kinds of thermodynamic uncertainty relations. But that being said, sort of in quantum computation, this is a bit hidden. So what do you think, guys? Do you think we're just far away from having perfect unitaries and being able to do quantum computation essentially for free, basically realizing the amazing feat of reversible computation?
Perfect what?
I don't know. Okay, clearly one answer from Natalia. Perfect unitaries, unitary gates. But I agree
Oh,
with you
those.
that it's yeah, it's a laughable idea. Yes. I don't know. Would anyone like to give that that question a shot? Give us a perspective.
Yeah, so I would actually say it's not a question of whether thermodynamics limits somehow our ability to do quantum computations, but it's more of an enabling thing. So I think to some extent, say Ralph's lecture, which showed that, or where he was mentioning based on some examples that entropy production is needed for good clocks. I think in a similar sense, entropy production is needed for having high fidelity computation. So this is somehow this cost that comes up. At the same time, I would also say at some point it starts limiting us. Say if we look on some piece of hardware and the entropy dissipation in that volume is too large, of course, you will have noise impacting your qubits depending on which platform you use. So I think somehow the grand challenge there is to somehow balance these two trends that are against each other. So on one hand, you want to have high fidelity, so you need to dissipate a lot. At the same time, high dissipation limits your ability to do computations due to the associated noise. And in the same sense, I think quantum error correction is quite interesting from that perspective, because also there, if you have, say, your error correcting codes, you have more redundancy to encode your information. You will also have more dissipation. And somehow, how do these two effects play out against each other?
I like the angle of, instead of thermodynamics telling us what we cannot do, actually enabling things, right? So enabling processes that might be useful for computation.
Mm-hmm. And maybe, Natalia, just to ask you a quick second question, like, as someone which is more, let's say, experimentally minded than all of us, someone who wants to show things in the lab, what do you make of these, like, nice, pretty, well, for me, nice and pretty bounds that we can come up with the entropy production on one side, the accuracy on another? Like, okay, they're nice things, but do you think that they are quote unquote physics, or how do you think about them as an experimentalist?
You mean if we can use them?
Yeah, are they useful? Are they insightful? Are they things we want to see in the lab?
Definitely. Well, we have a bunch of experiments that in which we are trying to reveal these bounds, and I think they're super important, because one of the things, even super practically minded as an experimentalist can be, if you think about computation nowadays, classical computation, right? We are so far from the thermodynamic limits, like by orders of magnitude, right? And the question is, even classically, let's forget about quantum for a sec, that I know it's difficult for us, but how can we, even get closer? And okay, maybe these bounds that we derive tell us, okay, that we are very far, but also give us a hint of how can we push these limits? Because even if we were to push these limits a tiny bit, in terms of energy consumption, we know that now with machine learning and other techniques, we are using insane amount of resources for computing, right? So even if we can push that limit at 1%, let's say, that would make a huge difference. So I think the more we understand what's bounding each system, and actually in the lab with devices that, right, that are, well, I'm biased for my devices, of course, but devices very similar to the ones that we use classically, we can say, well, the reason why we cannot operate them beyond such a limit is such and such, or maybe there is a way to do it, but it would be fantastic if we can find it out.
Very nice. Please, Tuka.
Yeah, I just wanted to say that I think the relationship that our area has with the notion of bounds is actually quite special, and I think it's quite nice, because in physics, bounds are actually not super common, right? Usually the way you do physics is with approximations, right? And your model may, the approximation can be good or bad, but this idea of bounding stuff is actually quite peculiar of quantum sciences and quantum information sciences in general. And I think this is really cool. So like the way you're phrasing, for example, saying, well, what bounds my system, right? In traditional, say, condensed matter, you'd say, what elements of my model or my approximation I may throw in a way that are bad. But it's a different way of thinking about it in terms of bounds. And I think that's really cool.
And it goes back a bit to the industrial revolution, right? And say, well, we want to build an engine. Okay, to what point can I optimize, and why not optimizing to a point or the other, right? So focalizes efforts in terms of.
Very cool. Do any of you wish to offer a comment, or for now you are all happy?
I mean,
Mark?
maybe just to add something that's slightly contradictory to what people have said before. I mean, I do think thermodynamics, in a way, limits computation, or quantum computation is in some sense a fight against thermodynamics in a very obvious sense, which is, what is error correction? I mean, it's a way of fighting against the ergodicity of natural physical systems to just thermalize and turn into mush, right? And so a quantum computer is just a very, very large scale many-body system that doesn't thermalize in the way that it should do. I mean, of course, it's not just that, it's also very special for many things, but I do think there is something quite interesting there about the quest to build a many-body system that really actually violates, in a way, the 0th or -1th law of thermodynamics, which is the system should come to equilibrium if they're big enough, right? And that's something that is obviously appreciated, but maybe still not fully kind of explored as a question in kind of thermodynamics or many-body statistical physics.
Wonderful. I'm super inspired by what has just been said. So I'm seeing that we have been up here for a while, and I do want to give the crowd questions, the ability to ask questions, any question on their minds, and then maybe I will get back to ask you one final one. So please, does the floor have any questions for our speakers, be that scientific questions, be that advice for how to pursue an academic career? We have quite an illustrious table, including the young Florian Meyer there at the end. So really, anything from advice to science, please give them your questions.
I can.
So recently, I've been in the last year of my PhD, or last 2 years, I've been working a lot on preparing thermal states on a quantum computer, and not thermal states of the Hamiltonian of the quantum computer. Well, because letting it evolve will just thermalize it, right? But what if I can give you an algorithm that would prepare a thermal state of any sort of thing? What would you do with it?
Gibbs sampling. I would do Gibbs sampling. No, but then you do the computation like with the thing. But yes, so I would use it for Gibbs sampling. But does anyone else have a fun? Gab?
I mean, I think you can do a lot, right? Because there's an entire branch in statistical mechanics, which is Monte Carlo simulations to simulate thermostates and look at phase transitions and this kind of stuff. And these are usually done for classical systems, or you have quantum Monte Carlo, which would be for some kinds of quantum systems, but not all of them. If you could do it for a generic Hamiltonian, I think in this whole business of many-body critical phenomena, you could spend 100 years just playing around with interesting physics in there.
I was going to ask a second question.
Yeah, go for it.
So yeah, this was my my point, was that basically can do a lot of things, and I was mostly concerned with the idea of just preparing the state and not really doing anything else with it. But so you would say you would use it to simulate possibly even other systems, and this kind of wraps in the idea of what Feynman said. You need a quantum computer to simulate any sort of other physics. So my second question is, if you have these states, for example, what would you find an industry application for using thermal states? Like you said, quantum Monte Carlo, but could you provide anything more specific, just as an idea?
Well, industry, I mean, I guess I'd have to think a little bit. If all you can do is really just prepare a thermal state and maybe not evolve it or something like this. The only thing that really comes to mind right now is more like, critical phenomena or equilibrium physics, let's put it this way, right? I guess for industry, it's usually more non-equilibrium stuff. So yeah, I don't think I have a great answer.
I can add something that I find interesting about these thermal state preparation problems, algorithms, is that, you know, you can ask yourself, do you want to prepare the actual Gibbs state of the Hamiltonian, so like the actual thermal state of the Hamiltonian, or do you want to prepare kind of the natural state that your system would evolve to if you were to expose it to some natural thermalizing dynamics with that Hamiltonian, which might not be the thermal state, right? It might not equilibrate. So you can really kind of ask yourself, which one of the two states do you want to prepare? Like in one case, you can do it like efficiently, and maybe it's the physical properties of those states that you're interested in investigating. So I think that's also an exciting perspective to have on that problem.
You're quite insightful.
Hi. So it's all quite nice what we're doing, right? Playing around with like thermodynamics and with like, this kind of effective theory that like, but do you think all of this can maybe bring us towards a, let's say, another paradigm shift, or does this move us into any direction where we would say we actually fundamentally gain insight into like expanding beyond where we are, or do you think it's rather we're better like properly understanding where we are at the moment? Like, do you think quantum thermodynamics, quantum information, and so on can bring us towards kind of new understanding, of, like more broader understanding of physics as well? And which areas or which directions do you think would lead us there, if at all?
Maybe I can give it's probably going to be a really weird rambling answer, but I mean, I think it's a really good question. I do think one of the, I see one of the main values of both quantum information and quantum thermodynamics is actually as a framework for understanding physics. And I think that's one of the most valuable contributions that the kind of quantum information revolution has made, is it has pretty much taken over every single field of modern physics as the framework and the language for describing you know, the cutting edge research that is being done. And that's true not just in, you know, AMO physics, which is kind of the area where this all started, but also in condensed matter physics, high energy physics, cosmology. Like if you actually look at what people in those areas are talking about, it's to a very large extent entanglement, error correcting codes. Like it's completely transformed the language. I think quantum thermodynamics in a much more modest way has at least provided me, and I think many colleagues also, with just a much better framework for understanding thermodynamics and statistical physics, which, let's be honest, is an area that lots of physicists are actually scared of, and many professional physicists I know that haven't worked in thermodynamics tell me regularly they've forgotten all their thermodynamics and they kind of don't really, they're kind of scared of it. So I think that's really, really valuable just as a conceptual framework, and that conceptual framework can actually really open up a new path to understanding new things. So I think, for example, you know, even though I don't work on it, like you know, high energy physics and kind of cosmology and these things, I mean, these people are kind of pushing the boundaries of what we might learn about the sort of structure of matter. And I think ideas from quantum thermo and quantum information are actually making an impact in that area. It's completely impossible to tell if it will actually go anywhere, of course. But yeah, that would be my kind of take on it anyway.
I can echo Mark's point, and I mean, we all have, of course, different motivations for why we do this, you know, why we do this research. But I think, I mean, I think it's good to be ambitious, right? And we have the perspectives where we might be able to build quantum computers. We might be able to do something really cool. And I think it's also very exciting that, as Mark said, like quantum information has given us really new tools and new language and new concepts to think about physics. So I think there's there's still a lot of excitement. I still have a lot of excitement for the potential that these concepts can give us to better understand physics. But of course, I think what's exciting is we don't really know what's going to come up, right? That's what we do, why we do research. And I think, there's going to be a whole spectrum of different outcomes and progress that we're going to achieve through kind of more incremental, or I don't want to say incremental, but like more down to earth, pragmatic improvements on what we have, or more far reaching, or simply just paving the next directions to find the next good idea to get to the breakthrough, right? It doesn't have to be right away, like tomorrow, oh, this is the big theory that we're waiting for, or something like that. So I think I am pretty excited in getting big things done, and I think it's good to be ambitious.
Yeah, go for it, Jeff.
Yeah, maybe, yeah, I also
echo what's been said myself. Like I'm personally extremely excited, and I'm even more optimistic in the sense that like I think that this is really the way to go to get a better understanding of nature. First of all, because like I mean, what we understand about nature comes through information that we can gather of the like of any experiment, right? I mean, we get data, and we had a chat with Gabriel before, and like about this. I mean, in the sense that like the important is what's in the data in some sense, no? I mean, and that's also the mantra that a lot of experimental groups have, no? I mean, because at the end of the day, I mean, we get data from like interaction with whatever surrounds us and whatever experiment. And now I think the real question is, how can we manipulate this information, okay, to understand better, and how can we connect this information that we have to like actual physical processes, right? That's basically what kind of thermodynamics does, okay? Like it's a first attempt to kind of like connect at least part of that information to something physical, like the change in the energetics of the system, right? And a quantum computer, in the best case scenario, where everything works, is basically a manipulation of such information, no, that you can prepare and manipulate in such a way to kind of like simulate any other system, right? So, I mean, in case you would be able to build a perfect quantum computer that can simulate everything, and basically you have developed quantum thermodynamics at the stochastic level, and you've tied it to information theory to the full stochastic level, then you can simulate everything, get the data out of this, and then interpret it physically. And I think that is I mean, what more can anyone want? I mean, that's the best shot that we have to understand more about nature, I think. That's my take.
Amazing. Any more comments, or people are satisfied? Oh, sorry, Maya.
Yeah, I mean, I have just a very brief comment, because it reminded me your question, Manu, about the panel discussion, I think 2 years ago at the Quantum Thermodynamics Conference in Vienna, where I think this panel discussion revolved to 80% somehow about the around an obsession about usefulness of quantum thermodynamics. And I really thought it's like it was an obsession, one can really say this. And I think here now this school, okay, I wasn't 100% present and can't remember everything, but I don't think the word usefulness was highlighted in any of the presentations. And I think that was very cool, because it is a foundational research field. I think most of us can say, yeah, they've had this insane breakthrough results. So all of us will have some smaller incremental results in understanding the theory better, which I think is perfectly fine. And one should somehow deal with that and not somehow try to make everything or sell it as something super useful. And I think this general attitude here at the school was, yeah, I think very welcoming. And yeah, I think that's somehow my comment to your question.
So let me just build up on that. I mean, I wouldn't say, because you made it sound like a number of results are not useful, but I would think
speak for yourself, Florian.
Yeah,
I mean, my papers, man, especially my papers with Florian.
No, but like my point is, you can be useful in many different ways. It can be useful in setting down the ideas for how to think further on a problem, right? So like, yeah, sorry, just wanted to put it that way.
Yeah, no.
They can be useful in different ways.
Yeah, I wasn't shitting on all kinds of usefulnesses.
The good Florian Meyer of Bern. So to carry on, Alberto Rolandi.
So I wanted to shift a little more discussion towards how the field is seen from outside, because in the past 10, 15, whatever years, the field has been growing a lot, right? And so definitely, one could argue it's been seen well from outside, especially from grant, for people that sign off grants. And but how do you see this going forward, rather? Like, do you see this, will it keep the same size? Will it keep growing? Will it go down? Like, what's the future like for quantum information, both on the foundation side and on the application side, because those have different, let's say, ways of attracting money.
I mean, I just want to give a partial answer to that. I think the way I would define quantum information is about the mindset, right? It's a way of thinking about systems and a language. And I think that we've already kind of achieved, we've already been able to kind of propagate the language to many other areas of physics, right? So I mean, people everywhere now know what a qubit is, right? And I think that's progress. So I think where it goes from here, I don't know, but I'm sure that, you know, it's here to stay, right? In the sense that we've really implemented this kind of way of thinking about things that now everyone in physics is really using. And I think that's awesome.
Okay, I'll take a more kind of a completely different approach to the selection, but I realized that as an experimentalist, for example, there are things that you say, well, I would move from some quantum information topics because there are big companies, right, like IBM or Google that or you know, big companies that there is no point in competing with them because the resources are just, you know, so you shift to doing things that are maybe more that try to tackle some of the bottlenecks that the companies are, you know, not so worried about, and they're going in that direction, and we kind of foresee that some of these are going to be bottlenecks, and we can work on those. Now, in terms of the quantum industry itself, I don't know, I'm seeing somehow like contradictory messages, right? So there are some quantum computing companies, there are a lot of quantum computing companies, more and more, and getting more and more money. On the other hand, I'm seeing some retraction of some small operations, right? Like I can see, like, for example, Microsoft leaving Australia. I can see, you know, like small signs of meh. And the question is, and I think this is a question for all fields and for all the fields that we develop in the future, is to what point, because it's true that, you know, the hype and so on help us to, as you were saying, to take our concepts like across fields and to make them important and to make people listen and to make governments listen and to make industry listen. But to what extent do we sell or oversell? It's and I'm worried that at some point, you know, it kind of has a backlash, and I hope that doesn't happen. But quantum computers are difficult objects to build, exactly because of what Mark explained, and we might need more time, right? So I think we might be in a position where we need to manage this carefully and also think of what would be the of this field and other fields in the future, and how should we engage with the public, policymakers, and other, you know, people interested in what we do, in order to you know, make be able to do what we like, which is science, in a way that it's positive and that we can engage really and do some well, positive, you never know, right? But what I mean is that we can actually identify some problems that are important and tackle them and engage the community on that in a way that allows us to succeed.
Thank you, Natalia. Do we have any more questions from the crowd? Perhaps some more junior members. So far, I've more or less seen 2 postdoc type people asking questions. I'd love to see PhD students, master students, undergrads asking questions. Philip Stammer, you have a lot of papers. The good sir in red.
Thank you. I would like to ask more of a foundational question. So in one of the lectures, there was this comment saying that the definition of field in quantum thermodynamics is still not very clear. There are many ways of approaching it. So my question is still like, what sort of questions should I mean, young researchers or like young experimenters have in mind to construct let's say, a universal framework or like a guiding principle to maybe make the field like self-consistent? Yeah, pretty much.
That's a tough question. So I mean, I can only give you some partial answer and probably very kind of like personal answers. I think that in some sense, moving like towards it's not just about like which correct definition. Like if I don't think there is like one single universal kind of like correct definition of what's heat, what's work, for example. And it's not even probably the most meaningful question, I would say, but rather like, I mean, one can like split the sort of like bookkeeping first law of thermodynamics into some sort of like what you call work, what you call heat. But the point is that, and I think all of these kind of like definitions and splittings and whatever, I think they have, you know, each one has its own merit and may look at different aspects and encapsulate some different aspect of information theory inside, okay? And especially this kind of can reflect into, I don't know, higher statistics, like what's going on at the level of fluctuation and so on. And it goes back also to the most important question which is like, what can you measure in the lab? Like, no, what kind of measurements can you carry out meaningfully? And this kind of like already is a physically kind of experimentally imposed set of constraints on what you can or cannot measure. And so which kind of definition you should use, or like which kind. Again, I think that the focus is like, what information do you have access to? How do you interpret, manipulate, and connect to what physical interpretation can you give it? Okay, and thermodynamics you have to really kind of like take as a set of what's allowed, like what constraints are you able to derive for the quantities that you are interested in, and that gave you the information at hand, right? But it's I don't think there is like one single, there's never going to be one single definition of heat and work that's going to be perfect or like, and that prove everything wrong. I mean, each has its own value. And in fact, I would say that I strongly recommend, like for a young scientist that approaches the field of quantum thermodynamics, to keep the mind open in this respect, no? And really read all of these definitions and see whether like when they apply, what they look for, and keep them like in high regard, all of them, because probably they also are very compatible with each other. They maybe look at different regimes and so on, but.
If you don't mind, I will leave this one to one answer just to keep us moving. We only have 12 minutes left to close off this hour. And with that, I will ask all of you one last final question, which I would like an answer from everyone, and one in two parts, which have nothing to do with each other. So in truth, it's two questions. First, we have some very young people in the audience. I would love for you to just give your 2 cents on what helped you along your journey as physicists, from undergrads all the way to where you are now. Is there something you wish you would have known? Is there something that you kept in mind that kept you going through the tough times, something like that? So some advice to our young members of the audience, and then something to take with us, perhaps over a beer later this evening. I will just remind the room that there are some really big open questions in physics, right? Like, why does the universe keep growing at an accelerating rate? The dark energy problem, the dark matter problem. You know, why is it that there is all this matter in the universe, which we cannot account for? How does life emerge from proteins, like cellular life? Does quantum thermodynamics, does metrology have any way to answer these questions? If yes, which one most excites you? Which is the one you go to bed thinking about? So just a piece of advice, and what is the big physics problem, the dream, the moonshot that you go to sleep dreaming about? We can start from Florian at that end.
So then the first question that you asked, I would turn this one around a tiny little bit. So you asked somehow what helped when you were young, and somehow, okay, whatever. So I think what helped me a lot somehow going from master's to PhD was to have senior people that would somehow care about my journey. I think this is like basically the main thing that was mattering, that somehow I was motivated to do stuff, and there were senior people who took that seriously and helped me, and somehow said, okay, look, there's this summer school, there's this conference, go there, or you should meet this person. And so I think this is to some extent surely the responsibility of us as young students to somehow stay on the ball, but it's also the responsibility, I think, of senior people, for example, at such conferences, summer schools at conferences, to talk to younger people and to somehow take them on the journey. And then as for the second question, a very brief answer, I think the connection between thermodynamics and, say, the emergence of life, I think there is some of the key conceptual connection that there is somehow that macroscopic system always has these emergent properties that microscopic systems do not have. And I think there's many people talking about this connection, and I've never seen any formal way of describing this. And I think it would be cool if, there's, at least in thermodynamics, which is a bit, quantum thermo, which is a bit easier to handle than biology, that there would be some ways to formalize these concepts. And now I give it to Gabriel.
Okay, so for the first bit, I would probably give advice that was actually given to me during my PhD, which is to do science is to be at the frontier of knowledge, which means that you're dealing with stuff that you don't understand, and not only you don't understand it, but people around you also don't understand it. So essentially, this means you're always confused, right? And I don't think there's a single day in my life that I'm not profoundly confused about something. And so good advice would be learn to navigate your own confusion, and find your safe harbors, and find ways to maintain. And by confusion, I mean kind of technical confusion, right? Not confusion about what you want to do with your life. That's a different question. But that would be my advice. Like, embrace the confusion, embrace the fact that you don't know stuff, that you will never know everything, and kind of navigate through it in a productive way. And for the second question, I would say the measurement problem. By far, the measurement problem is the biggest open problem in physics. So for those of you who don't know, the measurement problem is, why do we get random outcomes when we measure a quantum system, even though Schrodinger's equation is a deterministic equation, right? So if the universe satisfies Schrodinger's equation, there's nothing random in Schrodinger's equation. Why do we get random data when we measure? And I think this is by far the most important problem, because there's a lot of, pretty much every kind of paradox in quantum information and quantum mechanics, ultimately there's always a measurement in there. I don't think I've ever seen one kind of tricky paradox where there's not the notion of the measurement. It's always in the measurement part that things become tricky, and that's because you always have this issue with the measurement problem. So if I had to elect one problem, by far the measurement problem.
Okay, what helped me? I definitely wouldn't have continued in academia if it wouldn't have been for a lot of people that helped me, but not only like technically and support of my career, but actually challenges that I faced that I thought would not allow me to continue, and I thought I was the only one. And of course, you're never the only one. So if you're talking up with people and you go and say, I had this problem, and suddenly a lot of people had that problem, it's and you would be surprised, but there is a lot of people that are very willing to help in each of these, and that was a realization for me. And I think that as we become more senior as well, we have more tools to help in different aspects. Even, well, I think one starts to lose a bit of the technical detail of things and gaining maybe a bit tools to help also in other aspects of the career. So talk and reach out, and you would see there's some people there who would be happy to help. So that's one. In terms of big problems, I'm thinking a lot about this thing about how on earth are we coming back to something I said already, right? But how comes that we for us it's so difficult to compute when we are such good computers ourselves, right? I mean, efficient, and so how exactly nature has managed to make computing work and in a way that it's efficient, and that's something that I've been thinking quite a lot, that I find super interesting. So how does, and inspired by other people as well, right, on the things of what is needed to learn, for a system to learn, and how is it connected to entropy, and how does a system, you know, acquire, and that goes across all in nature, right? Everything in nature learns to some extent. It's so that's yeah, interesting. I don't know what experiments to do yet. If you have an experiment, I will do it.
So yeah, good answers so far. So obviously the pool of cool things to say is dwindling as we move along the table. Okay, so the first one, yeah, I mean, I think one thing that was incredibly helpful for me as a young scientist was to kind of to find my community. I would maybe phrase it that way. So I would say, find your community. That is my advice for you know, the younger people, and that could mean lots of different things. That can mean like finding a community in terms of a kind of research community of many people. It can also mean just a few people that you actually get on with, and you can you know, you can talk physics with, and I think if I look back at the history of my career so far, and you know, the stuff that I've done in science, it's really a story of relationships that I've had with different people. I'm personally not one of those people that can just sit in a room and work on my own. Everything that I've ever done that's been good and enjoyable has been actually in conversation and a relationship with one or more other people. So, you know, physics is a social activity. So try and enjoy that part. And if you're not enjoying that part, you know, find some other people to do it with, I guess. Oh yeah, and don't think about physics before bed, because you won't be able to go to sleep. That's the other thing that I learned way too late, because I'm not a good sleeper. And then in terms of like, okay, connections with the really big open problems. Well, one thing that I've always been fascinated with, and I think, you know, it's not very original, is you know, the kind of emergence of irreversibility, like why we see irreversible behavior in the macroscopic world when you know, the underlying equations and laws and everything are kind of deterministic and reversible. It's obviously very connected with the measurement problem that Gabriel mentioned, but it's also, you know, it's something that people are still studying very actively in the context of, you know, how does closed quantum systems thermalize? What are the precise conditions for this? What are the more refined things that we can say about thermalization? For example, thinking about correlations between different kind of events in time within these kind of many-body systems. That is one kind of very interesting emerging frontier in many-body physics that actually has contributions both from kind of quantum thermo people studying black hole physics. So I think that is a really interesting emerging frontier of really fundamental physics where quantum thermodynamics ideas are actually playing a role. But yeah.
So a lot of great things said already. I can only second all of that. Of course, it's tricky to give advice, because I think academia is also one of the places where, sure, you can give advice, but at the end of the day, also each trajectory is a bit different. It depends on your constraints and everything, on kind of your motivations, on your drive. I'll just add one thing that was very helpful to me, you know, before getting a permanent position, is that one thing for your mental health. Well, one thing that for me really helped was to kind of go through the mental process of saying, wait, I have like a PhD. We all, you know, you all will have like a PhD in the technical, in a very, you know, very technical matter. You are professional generic problem solvers. You're useful to society also outside of academia. It's perfectly fine and you can do great things outside of academia. And like for me, going through this process of, well, actually, I could actually also do great things outside of academia. Even if you stay in academia afterwards, that was actually something that was very helpful in my mind in during those, you know, years of where you don't have yet a permanent position. So that would be kind of a very just pragmatic thing that helped me. For the big open questions, I think it would be really cool to build a quantum computer. You know, I think that's it's kind of a boring answer, but like, I think that's one of the things that would be really cool. And I think it will also be really cool to really understand some theory of quantum gravity that's better than, you know, that's more simpler, that's nicer, that's kind of maybe uses more concepts of quantum information than we have now. So I think that would be exciting to see both of those happen.
Yeah, so, well, I mean, most of the questions have, I mean, my answer is gonna look very similar, but like what I have to say is that like, for me, it was, I think, the crucial part was interactions. Like, never be afraid of like actually interact as much as you can with like your peers, with people that you have esteem for, okay? And more senior, like whoever, like never be shy, okay? At the conferences, for example, this has been for me the most fruitful kind of like a type of events where like collaboration started. I met people that I'm still friends with today and collaborate with today. And as Mark said, find your own community, in the sense that it was for me, I mean, for example, when I met this community of quantum thermo, quantum info people, I kind of like, I met with amazing people, okay? So I think this is a very good field. And I think the last piece of advice is like, keep being passionate about it, like be enthusiastic about doing physics, because I mean, this is probably the best thing in the world, let's be honest. I mean, it's for me. So never lose this kind of enthusiasm, I think, because I mean, life can get very hard, clearly, but I mean, we are kind of blessed to have this occasion, and I think that keeping this kind of mindset will help you a lot. And on a more practical kind of but connected note, I would say that what personally helped me kind of like in my career was applying to grants. I mean, this is so not just stick like to do only papers, but I know it's very hard, but like be active and like try to apply to grants a lot, which kind of also helps on a scientific level. At least it was for me. Like if you take it with the correct attitude, I think what I think is the correct attitude, which is like really kind of like tidy up your thoughts and put them in perspective, like to come up with like a longer plan. Because maybe sometimes when we work on like a specific paper, it's just like the horizon of like the scientific endeavor is like very close, but like really like applying to getting into like applying to grants forces you to kind of like put the horizon a bit more forward, at least, no? So I think like be active, be enthusiastic about this, like doing physics, and that's it. And about the big problems, I think it's unsurprising. I mean, it's something that has been said, but more I would frame it more as understanding better the quantum to classical transition. Which is related, of course, to the measurement problem. It's, of course, related to like the problem of thermalization or equilibration in general. And I mean, unsurprisingly so, like I really enjoy to collaborate with these people, and probably because we have kind of the same kind of long-term goal. So yeah, basically that's it for me.
Well, this has been a really, really very enjoyable panel for myself, at least. I hope it has been for the whole crowd. So let's thank our speakers. And so with that, this brings us to the end of Calypso 2024. And I would like to just thank some people like Dr. Tony Apollaro of the University of Malta, really our saint. And without him, we would have not done this. The other locals like Manu Schwartz, Hans Mirko Concilio, Evan Camilleri, Alessandro Strumner, who is not a local, but is a... and then I would really just thank all of you for coming to Malta, to the Maltese students for showing up. I know it's not easy. So yes, thank you very much. It has been really a privilege. To the speakers as well. It has been really such a good week. I've enjoyed it tremendously, and it's only, you know, thanks to the great vibes that we all create together. So I hope to see you again on the island of Malta sometime here. Cheers, guys. Cheers, thank you.